Hello everyone and welcome back. We are going to tackle the FRQs, or maybe not welcome back. Maybe this is the video you're choosing to watch first. If you haven't seen the multiple choice, check that one out. Leave a like. Remember to hit that bell notification icon. Let's get into the exam review. Alrighty, so FRQs, one long FRQ, one short FRQ. We're going to start off with the long FRQ. Let's start off just by reading this bolded thing at the top here. For parts of the free response question that require calculations, clearly show the method used and the steps involved at arriving your answers. You must show work to receive credit for your answer. Wow, that means I should probably show work on these if I used work and not just write down the answer, because Mr. Stelzer, me, is not going to give you credit if you don't show your work. You have to show your work for your questions. That happened a few times on the last test where people got answers right, but they didn't show work. If you don't show work, I don't give credit. Okay, so a student is given the task of determining the concentration of copper 2 sulfate solution using two different procedures, precipitation and spectrophotometry. Those are both labs we've done so far. For the precipitation experiment, the student adds 20 milliliters of 0.2 molar barium nitrate to 50 milliliters of copper 2 sulfate, and the reaction goes to completion. A white precipitate forms. The student filters the precipitate and dries it overnight. The data is given in the following table. So first off, we need to write a balanced net ionic equation for the precipitation reaction. Let's just start off with trying to get an actual reaction in. We're combining barium nitrate, BaNO3, with copper sulfate, copper 2 sulfate, CuSO4. The products are going to be barium sulfate, BaCO4, and copper 2 nitrate, CuNO3, 2. So in a net ionic, we cancel out spectator ions. We know both of these are soluble. The question is, which of these two is the precipitate? And this goes back to just if you know SNAP. Nitrates are always soluble, so it's not the copper 2 nitrate. It's the barium sulfate that's the precipitate here. So let's write that reaction. It's going to be barium 2 plus SO4 2 minus yields BaSO4 solid. Okay. Copper sulfate. All right, calculate the number of moles of precipitate formed. All right, to calculate the moles, we need to go to this data table. So this is something you've done in your lab. We've done a precipitation reaction. We measured the mass of the dry filter paper. We measured the mass of the dried filter paper and the precipitate. To get the amount of precipitate by form, it's going to be this number minus this number. So we're going to do 1.136 minus 0.764, and that gets us 1.136 minus 0.764, and we get 0.372 grams. We don't want grams, we want moles. So if we have 0.372 grams, converting to moles, the precipitate is barium sulfate, so we need the molar mass of barium sulfate, which means we need to go to the periodic table. I do not have mine out, so let's go to this one. We still have things from the last. That's going to delete everything. I don't want to do that. All right, looking for barium sulfate. Barium is 137.33. Sulfur is 32.06. plus 4 oxygens. Each oxygen is 16. 137.3, I forgot a 3 here, plus 32.06, plus 4 times 16, and we get 233.39 grams per mole. Let's go back to this. So there are 233.39 grams per 1 mole of barium sulfate. So 0.372 divided by that answer, we get 0.0015939 moles of barium sulfate. Let's round to sig figs. The sig figs for this question looks like it's going to be 3 sig figs. So it's 0.00159 moles BaSO4, and that's our answer. Sig figs were not checked on this FRQ, by the way. We need to calculate the molarity of the original copper 2 sulfate. So the volume, molarity, let's start off with the molarity equation. Molarity, concentration, is moles over liters. We just found the moles. The moles is 0.159, so that's going to go there. So 0.0015939. I'm going to use my unrounded answer. The liters we're going to get from the data table or the problem statement. We started off with 50 milliliters of copper 2 sulfate. Or actually, I guess I skipped a step, but it doesn't matter anyway. This is the moles of barium sulfate, but I'm trying to get the moles of copper 2 sulfate. So I guess the first thing to do was to go 0.00159 moles of barium 2 sulfate, and according to my reaction I made, for every 1 mole of barium sulfate, we used up 1 mole of copper sulfate. So it's a 1 mole to 1 mole ratio. So we're going to get the same amount of moles of copper 2 sulfate. So it didn't actually matter, but I almost skipped that step, and it could have cost me. I have actually taken practice. As a teacher, I've taken a practice. My first year I took a practice exam. And the one question I got wrong on the exam was me not doing that. Me not remembering or forgetting to actually do the stoichiometry part of the question and go from moles of one thing to moles of another thing. It's a very easy step to miss, but it can cost you. All right, the liters of copper 2 sulfate, we had 50 milliliters, so 0.05 liters. So divide that by 0.05, and we get 0. Sig figs are going to be 3 sig figs still. So let's write the full number first. 0.031879 molar, rounded to sig figs, 0.0319 molar. Great. For the spectrophotometry experiment, the student first makes a standard curve. The student uses a 0.1 molar solution of copper sulfate to make 3 solutions of known concentrations, 0.0, 0.05, 0.03, and 0.01 in a 50 milliliter volumetric flask. All right, what's actually, before I do this question, what's really interesting to me is look at, so the process with spectrophotometry is first we need to make a curve of known concentrations, and we can measure absorbance versus concentration, and we can make a calibration curve, and then we can plug in an unknown concentration, and wherever that whatever that absorbance is, we can match it up to the line and get the concentration. What's really interesting is the concentrations are 0.05, 0.03, and 0.01 for the copper sulfate. The copper sulfate concentration I found over here was 0.03. So that's a little bit of self-verification. I feel like I got that one right because those calibration points make sense for this concentration here. It's like in the range of those calibration points. But anyway, let's do the question. Calculate the volume of 0.1 molar copper 2 sulfate needed to make 50 milliliters of 0.05 molar copper 2 sulfate. This is dilution, so we're going to use M1V1 equals M2V2. Our initial concentration is 0.1 molar, and we are trying to solve for the volume of that 0.1 molar needed. We're trying to end up with 0.05 molar, and specifically 50 milliliters. So do 0.05 times 50 divided by 0.1, and we get 25. We need 25 milliliters of the 0.1 molar. I guess sig figs 25.00 milliliters because everything is 4 sig figs. Briefly describe the procedure the student should follow to make 50 milliliters of the 0.05 molar copper 2 sulfate using 0.1 molar of the copper 2 sulfate, a 50 milliliter volumetric flask, and other standard laboratory equipment. Assume that all appropriate safety precautions will be taken. The standard curve given below is part of the next question. All right, so D was the math behind making the solution. E is now the lab procedure. How do you actually go out and make that solution? So we don't have to make the initial solution. We already start off with the 0.1 molar copper 2 sulfate. So first thing we're going to do is, I'm going to say, using a, let's say a 25 milliliter graduated cylinder, using a 25 milliliter graduated cylinder, measure 25 milliliters of the 0.1000 molar copper 2 sulfate solution, and then pour that into a 50.00 milliliter volumetric flask. Alright, I realize you guys might actually have to read this, and it's kind of hard to write on this thing, so let me try and make my handwriting a little nicer. Alright, we've done this a couple times. So how do we make a solution in a volumetric flask? So first, measure out the correct amount you need, pour it into the volumetric flask. The second thing I'm going to do is I'm going to rinse my graduated cylinder with a small amount of distilled water. And I'm going to pour that into my flask. Just to make sure that all of that 0.1 molar ended up in the volumetric flask. Next thing I'm going to do is I'm going to slowly add distilled water to flask until we reach the 50.00 milliliter mark. And you know what, just for fun, let's say we're going to use a dropper or a pipette, just something to go drop by drop when in the neck, which is the skinny portion of the flask. Last thing, I skipped 4. Last step, let's cap the volumetric flask and just invert it a couple times just to make sure everything is cohesively mixed together. Cap the flask and invert. We don't want to vigorously shake because then like it can go everywhere, the cap can break. And invert, I'm going to say a couple of times to ensure solution is homogeneous. That is like a real step like we need to take. I don't know if you remember back to the spectrophotometry lab, but when you made like a solution in a graduated cylinder, you can kind of see that like some parts of the graduated cylinder were like more blue than other parts. It's because it wasn't mixed thoroughly enough. In a volumetric flask, we get an advantage of being able to cap it, so we can invert it a few times to mix it very easily. All right, that's the correct procedure. The absorbance for the copper 2 sulfate solution of unknown concentration is 0.219. Determine the molarity of the solution. Okay, so when we do spectrophotometry, now we have reached the point, I don't know if I still have my thing up here. We've reached the point where now we've plugged in the unknown concentration and we're getting an absorbance, and we're going to match that up into a concentration. Whenever you get one of these graphs of absorption versus concentration, the question that immediately follows it is like 99% likely to be, can you read this graph? So we're given this graph and the question's asking, what is the concentration when the absorbance what is the concentration when the absorbance is 0.219? So let's find 0.219. This is I moved it. So it looks like this is 0.3. So 0.219, that's really close to 0.2. So like a fifth of the way up to 3. I would go like right there. Match that over. I would say like right there. I'm going to be as accurate as I possibly can. And then maybe like a little lower, maybe like there, and go down, go like there. This is 0.03. I would say I'm 0.036 molar. Closer to the 0.04 than I am to the 0.03, so let's do 0.036 molar. You do have to give it your best shot to read the graph. I know it's kind of hard to see, it's kind of hard to but you're usually given an accepted range. But what's not part of this accepted range is if you go to like 0.03 or just say 0.04. You have to make an attempt there. I would say 0.036. A second student performs the same experiment. Actually, let's go and what did I say for my other solution? I said 0.0319 molar with precipitation reaction, so I'm in the right ballpark. And 0.036 with spectrophotometry. So we got the similar concentration in the two ways. That's what this question was about, finding this concentration of an unknown solution in 2 different ways. All right, I'm dragging on. Let's continue. A second student performs the same experiment. There are a few drops of water in the cuvette before the second student adds the copper sulfate, the solution of unknown concentration. Will this result in a copper sulfate concentration for the unknown that is greater than, less than, or equal to the concentration determined in part F? I'm going to say it's going to result in a less than concentration. So the drops of water, and the reason is the drops of water will dilute the cuvette, meaning the absorbance will be less than what it should be. And according to this graph, if absorbance goes down, then concentration goes down. So So concentration will be less than as well. All right, is that it for this FRQ? There it is. Cool. All right, let's move on to FRQ 2. Let's go through this one quick. I feel like I'm going a little slow. Identify the species that was reduced in the titration reaction. Justify your answers in terms of oxidation numbers. All right, so we have this reaction. We start off with 0.139 sample of oxalic acid, and then we're titrating it with this. No, that's oxalic acid. We're titrating with potassium permanganate, which has a dark purple color. The balanced chemical equation is above. Identify the species that were reduced in the titration reaction. All right, so we need to do oxidation numbers, justify in terms of oxidation numbers. So we have +1 here, we have -2 in that oxygen, +7 in this manganese. I went a little quick. A total minus charge of -8 in the oxygen, so this one manganese needs to be +7 so that we end up with a -1 charge in total. In the oxalic acid, we have -2 in the oxygens for a total minus charge of -8. We have +1 in the hydrogens for a total charge of +2. These two carbons need to be +6, which means each carbon is +3. In carbon dioxide, we have -2 for the oxygens, +4 for the carbon. We have -2 for the oxygen and water, +1 for hydrogen, and +2 for the manganese. So we're looking for something that gained electrons. It looks like manganese gained electrons because it went from an oxidation number of +7 to +2. Gain electrons reduced, because we're looking for the thing that's reduced. That is the GR. In Leo, the line says GR. And +7 to +2, we went down in charge, which means we took in more electrons. The student uses a 50 milliliter burette. I don't care about the faint lavender color. We're looking for the initial and final readings on this burette. Okay, so enhance. So we're in between 3 and 4. So this is 3.1, 0.2, 0.3, 0.4. I would say we're like halfway in between 0.3 and 0.4. So I would read this as 3.35 milliliters. On this one, we're in between 29 and 30, 29.1, 0.2, 0.3, 0.4, 0.5, 0.6. I would say we're like halfway in between 0.5 and 0.6. I would read this as 29.55 milliliters. For reading a burette, you can go halfway in between tick marks. You can either go to the nearest tick mark or the nearest halfway in between a tick mark. If, let's say, this was at one of the tick marks, if it was right at 0.6, then the reading on the burette would be 0.60, because we still keep that last digit for significance. This 29.55. Okay. And then use that to determine the volume of potassium permanganate. So we're going to take the difference between these two. The final reading was 29.55. The initial reading was 3.35. The difference between those two, 29.55 minus 3.35, is 26.20 milliliters. Significant figures are checked for this one. We have to keep that 0.0 because that's the sig fig rules for addition and subtraction. If both of these are to the 100th, we keep our digit to the 100th for addition and subtraction. All right, given the concentration of potassium permanganate, scroll, given the concentration of potassium permanganate was 0.0235 molar, calculate the number of moles of permanganate ion that completely reacted with the oxalic acid. All right, first things first, for every 1 potassium permanganate, I get 1 permanganate. Potassium permanganate gives me 1 potassium and 1 permanganate. So if I find the concentration of that, that equals the concentration of that. All right, molarity equals moles over liters. We have to know the concentration equation. Whenever we're asked for molarity or concentration, it's always that equation, unless it's dilution. All right, the concentration was 0.0235. We're solving for moles. I don't know why I did that. And the liters we're going to get from our answer in the previous question. This is the amount we used, 26.20 milliliters, which is 0.0262 liters. So 0.0235 divided by, or multiplied by 0.0262, we get a mole value of 6.157 times 10 to the negative fourth mole, rounding to sig figs. It is going to be 3 sig figs, so 6.16 times 10 to the negative fourth moles. Is that right? Moles over liters, yeah. The student proposes, for part D, last one, the student proposes to perform another titration using a 0.139 gram sample of oxalic acid, which I believe is the same amount of oxalic acid. Yep, so the same amount of oxalic acid. But this time using 0.00143 molar potassium permanganate. So if we're doing math back at home, that's like half the concentration. 0.00, is it? It's like less than half. It's like, let's do that number. So 0.0235 divided by 0.00143. That's a 16th of the concentration of potassium permanganate. So we are severely lowering the concentration of potassium permanganate. Would this titrant concentration be a reasonable choice to follow the same procedure and use the same equipment as before? The answer to this is no. That is way too small of a concentration of titrant. When we had a concentration that was 16 times higher, we used 26.20 milliliters. If we put something that's 16 times lower, we're going to have to use 16 times as much titrant to get to equivalence point. If we double the concentration, or if we have the concentration, that's already too little concentration because we've already exceeded the capacity of this burette. This burette's capacity is 50 milliliters. So this is a question where we can absolutely justify mathematically. So if you wanted to set up another M1V1 equals M2V2 and solve for how much you need, you can do that. But I'm just going to say no by lowering the concentration to that extent. The amount of titrant needed would far exceed the capacity of the burette. So that's the answer. That's a tough one. That's a really tough one to see because of all of these, complicated looking numbers. But compared to what we were before, we just can't do that. The concentration is too low. We've already are using most of our burette. We're going to be over the capacity of the burette. If we're over the capacity of the burette, it's a bad experiment. Our burette should always have enough titrant to titrate our thing, or else we're very likely to mess up readings. Alrighty, there is the FRQ. Quite frankly, I feel like I was a bit mean with last year's class with this entire test. I felt like this test was hard. I feel like I gave them some pretty tough multiple choices and some pretty tough FRQ problems. Maybe I was mad at them. Hopefully I won't be mad at you guys. I still have to make your exam, mostly. I've already done some of the stuff. So we will end it there. I hope this helped. As always, feel free to ask questions in class, get some clarification. That is it for this one. I'll see you guys in the next YouTube video come Unit 5. All right, bye.